So, welcome everyone. Today we have Sean Hartnoll telling us about entanglement and emergent space from large matrices. Over to you, Sean.
Great, thanks a lot. It's a pleasure to be here, even if remotely. And so, mostly I'm going to talk about this paper with my student Alex Frenkel that just appeared somewhat recently. And some of the groundwork for that was in these previous two papers with my earlier student Shijie Han and another paper with Alex. So the broad motivation is that I would really like to understand the meaning of this. I guess we could now call it Bekenstein-Hawking, Ryu-Takinagi type entropies, which in theories of gravity, there's some contribution to maybe an entanglement entropy that goes like the area over G Newton in theories with gravity. And that this is a especially large and universal contribution to the entanglement. And it's quite large because when G Newton is small and the perturbative limit, it gets big. And so it's rather non-field theoretic in nature from that regards. And so what I'd like to start working towards are, I'd like to be able to have concrete models, so explicit models, explicit microscopic models of emergent space. So normally, I mean, entanglement entropy is a very powerful tool and very well understood in cases where the locality, be it in the quantum field theory or on a lattice, is there in the starting Hamiltonian. But I believe that this kind of entanglement is more associated to cases where the space is not pre-existing, but emerges together with the fields in the space. Okay, so I'd like to understand how to think about entanglement or in situations where locality is emergent rather than given. And for that, I'd like some explicit models. Okay, and so the models that we're going to talk about today are models of space from matrices. Of course, it's very well known that matrices want to build space going all the way back from the C=1 model through BFSS and n=4 super Yang-Mills and so on. What's going to be special about the kind of models that I'm about to talk about is that the matrices are going to be semi-classical. And that's going to make it much easier to get a handle on things. And in particular, semi-classical matrices are basically going to amount to a non-commutative geometry. That I'll describe in a minute. Okay, so what I'm going to do, the thread of the talk is I'm going to write down a completely explicit model, matrix quantum mechanics. This matrix quantum mechanics is going to have a semi-classical state that's going to describe a fuzzy sphere. And then I'm going to describe how to partition the matrices in a way that reveals the emergent locality of the system. I'm going to calculate entanglement, and we're going to see that there is a large contribution to the entanglement that's somewhat analogous to this contribution. Okay, so I say analogous because the emergent geometry that I'm going to discuss, we're going to have an emergent Maxwell field, not emergent gravity. Okay, but so in some ways, the space that's going to emerge is more like a brane world volume rather than a dynamical spacetime. But nonetheless, I think it's going to be quite instructive. Let me first ask: can everybody read this handwriting? Does it work?
Yeah.
Yep.
Yeah.
It's okay.
Yeah.
Okay. All right. Okay. So that's the plan. Okay. So to think about entanglement, wave functions in models of emergent space, and right. Good. So let me just let's write down the model. So there's going to be a Hamiltonian. Okay. That's going to be trace, where this is not a quantum mechanical trace, it's a matrix trace. And it's going to be a half sum over I, pi I squared plus V of xi, where xi, a, b, so I is going to be 1, 2, and 3. So there are 3 matrices, and AB runs from 1 to n. And so these are 3 n by n Hermitian matrices. Okay, and so this trace is over these AB indices. And then the pi i's are the conjugate momenta. Okay, so that's a pretty generic matrix quantum mechanics. And I've chosen with three bosonic matrices. And so this model has, I'm going to gauge the UN, this model has a UN symmetry. So there's a UN symmetry that I'm going to gauge. So the generators of the symmetry are GAB to I sum over I xi pi I, right, as usual. And so this commutator is a classical matrix commutator. It's not a quantum mechanical commutator, right? And so the statement that the symmetry is gauged is that physical states are annihilated by this symmetry. Okay, that's the class of models. And what I'm going to do is choose a particular potential. V of x is going to be a quarter nu, which is some parameter, epsilon I jk xk plus I xi xj squared, where squared means, of course, that you contract these I and j indices. Okay. This is actually quite a well-motivated potential. So this is the bosonic sector of a supersymmetric theory. Of a SUSY theory. And this SUSY theory is sometimes called mini BMN because this potential and the structure also appear in the BMN matrix quantum mechanics, which is a maximally supersymmetric deformation of BFSS to include a mass term. Okay, so these are, you can think of this as a very simplified model of some of the physics that goes into this well-known BMN model. If you don't know what the BMN model is, it also doesn't matter. I'm just saying this potential is somewhat well motivated. Okay, and so that now I've given you the model explicitly. Okay, so there are, let's think classically, it's a Hamiltonian for a bunch of matrices, and they have this potential. Okay, that's the model that I'm going to look at. This is clearly, there is no space. This is a 0+1 dimensional model for 3 matrices. Okay, so the classical ground states. So I should say I'm not going to be considering the supersymmetric model today. I don't think it matters too much for what I want to say. We're just going to think about the bosonic sector. Okay, so this model has a classical ground state. So we're going to start classically, and what we're later going to see is that this nu, which is the sort of mass deformation parameter, the limit where nu is large is a semi-classical limit, and that is the limit we're going to be working in. So it is going to be reasonable to start with the classical ground state. So the classical ground state is just 0, the momenta all vanish, and the x's sit at the minimum of the potential. Because the potential is an exact square, it's clear that the minimum of this potential, so the classical ground state, is the minimum of the potential, and that's matrices that obey xi classical, this is the classical ground state, or classical ground state, classical equals I nu epsilon I jk xk classical. So matrices that obey that are the zeros of this potential, and because it's a total square, they're the minima. All right. So this is obviously very recognizable as the SU2 commutation relations. Remember, these are n by n matrices. This is the SU2 commutation relations. And the solutions to this are called fuzzy spheres for reasons that I'll now explain or remind you. So what we're going to look at is sort of a choice, actually. So we're going to look at the maximal fuzzy sphere solution. I'll tell you why it's called a fuzzy sphere in a minute if you don't know already. So you look at the maximal fuzzy sphere solution, which is when the x's are given by the n-dimensional irreducible representation of SU2, right? So x. So we're trying to solve. That's the classical state obeys this to minimize the potential, and so a solution of this is that the x classicals are nu times some ji's, where ji is the n-dimensional irrep of SU2, right? It's the SU2 algebra, and we have n by n matrices, and so this is sort of the natural thing to do. So let me write this down extremely explicitly. So J3 is a n by n matrix, and it looks something like this. I'm going to drop some minus ones. So think of this to leading order at large n if you want. So n over 2, n over 2 minus 1, all the way down to minus n over 2, right? That's like your z of the SU2. And then there's raising and lowering operators, in particular J minus. It's actually n minus 1 over 2, but that doesn't matter. J minus has zeros along the diagonal, and just below the diagonal here, there's a square root of n minus 1, and the general entry is the square root of n. You know what? That's a bit too small, isn't it? Why didn't I just the general entry is square root of n minus n, and then it goes back to n minus 1 at the other end. And then there's a j plus, which is the conjugate of j minus, right? So there are three. This classical ground state is just three very explicit matrices. And obviously, I've picked a gauge here in the sense that any SUN rotation of these matrices will also be okay. All right. So, but in some choice of gauge, this is a completely explicit solution of these equations, which are the classical ground states. It's a classical ground state of this model. Everyone happy? Any questions? I'm very, very happy to take questions as I go.
Will you explain later why you chose this particular representation?
Not really. So why don't we come back to this at the very end? It's just in a way, I just want to have an emergent geometry that I can make some points of principle with, and it actually wouldn't matter too much which one I choose. But indeed, in the best setting to be doing this would be the supersymmetric model, where these all of these states survive in the quantum theory. But there is tunneling between them and so on that is interesting, but it's not what I'm going to talk about today. So I'm just going to be considering semi-classical fluctuations around this classical state, and I'm just choosing one of them. But we can, I'm definitely, maybe at the very end, very happy to talk about that at the very end. It's certainly a legitimate semi-classical state, which may be metastable in the purely bosonic, is in fact metastable towards tunneling in the bosonic model, but it's a good semi-classical state. Right.
In the bosonic model, are the ones that are reducible representations at lower energy or higher energy than this one?
Yeah. So so actually we looked at this in this paper where we did some numerics and so on in this model. And so in the bosonic model, indeed, there's a sort of a collapsed state where the x's are basically zero. That is the energetic ground state. because there are large fluctuations about the fuzzy sphere that have a large energy that push it up. In the supersymmetric model, those fluctuations get cancelled, and in the supersymmetric model, I think all of these spheres are ground states.
Yeah.
In the quantum.
That makes sense.
Yeah, thanks. And I think this is especially well understood actually in the full BMN theory. There are actually dual geometries are known for different choices of these spheres. So, right, so that's why I'm not worrying too much about the bigger metastability question, because I'm just, the properties, the semi-classical properties of these states don't depend too much on, they don't depend on how they're embedded in the bigger theory. But we can definitely come back to this. It's a fair question. Okay, so this is a classical state. That's certainly true. Okay, so now just to remind you or to tell you why there's a fuzzy, why this particular choice of matrices can be thought of as an emergent sphere. So to see the emergent geometry in this setting, we can look at fluctuations about classical, so still classical. We can take these classical ground states and just perturb them by some other matrix AI. And let's suppose you want to understand the spectrum of these fluctuations. And so, as usual, it's very useful to expand the fluctuations in some kind of basis. And the natural basis is something called a matrix spherical harmonic. So the AI, these fluctuations, can be expanded in terms of some coefficients, AI Jm, in terms of some basis of Hermitian matrices, y hat Jm, right? So this is some basis of matrices, and these are called the matrix spherical harmonics. And so what are these? They are matrices, and what do they obey? They obey that Ji commutator Ji. Remember, Ji are the generators of the irrep. Yjm equals J plus 1 y hat Jm, and the commutator of J3 with y hat Jm is M y hat Jm. So these are, of course, very analogous to what spherical harmonics obey. And those of you that know anything about non-commutative geometry, you know, this is the usual thing that derivatives become commutators. So, but we don't actually need that. So these equations define these matrix spherical harmonics. Oh, an important point. So M goes from J to minus J as usual, but J doesn't go all the way to infinity. It's cut off at n minus 1. So these matrix spherical harmonics have a momentum cutoff. They have a maximal J. And that makes sense because they're just n by n matrices, so there's not room to go higher. Okay, so these turn out to be a very convenient set of matrices, and you can expand your perturbation matrices in terms of these matrices with some coefficients. You can plug this into the Hamiltonian to get an effective Hamiltonian for the fluctuations for these coefficients. Remember, I gave you everything's completely explicit. I gave you the Hamiltonian before. Now, what you can do is using these same coefficients, you can regroup them into something that looks geometric. So we're going to now define a field AI of theta and phi as a sum over Jm. You take the same coefficients, but now instead of matrix spherical harmonics, you put the normal spherical harmonics there. Okay, and these sum still only go up to n. So this is certainly an object I can build, right? So for every matrix A, I decompose it in terms of matrix spherical harmonics, and then I build a corresponding function on a sphere by using the same basis, but replacing the matrix spherical harmonics with the usual spherical harmonics. Okay. And so it turns out that if you do that in the Hamiltonian, you can just do this in the Hamiltonian. And okay, there's one more step. This AI, you split into a sort of a radial component and and a perpendicular component. So I'm going to have, sorry, so split AI into a perpendicular and a sort of a transverse and a parallel component with some vector n, where n is like a x, y, z, a unit vector pointing out. So we have a scalar that's going to be a dot n, and then a b, which is a cross n. N again is just a vector that contracts with this in a, yeah, with that index, and b has a corresponding field strength, which is n dot the curl of b. So this okay, I'll show you what this means in a second. These basically, there's going to be a sphere. The phi are going to be fluctuations of the sort of transverse fluctuations of the sphere, and f is going to be f theta phi, a gauge field, a maximal field strength living on the sphere. So in terms of these quantities, the same Hamiltonian that I wrote before turns out, yeah.
Were the A's appearing in that expression of this AI of theta and phi?
Yes, that's correct. This A here. Yes. And n is a vector orthogonal to the sphere.
Some fixed vector.
It's n. It's something like x, y, z normalized, where x, y, and z are written in terms of theta and phi.
Okay.
It's not a, yeah. That makes sense.
Yes.
Yeah, great. So then that Hamiltonian that I had before, okay, so you just take that Hamiltonian, you decompose the matrices like that, you rewrite it like this. The Hamiltonian is just equal to, okay, there's no approximations, an integral over the sphere, a half the momentum conjugate to pi, to b, sorry, the momentum conjugate to phi, a half f minus phi squared plus a half grad phi squared. Okay, I'm sorry. So yeah, sorry, what I've just wrote is true in the n goes to infinity limit. Okay, and so what this is, I'll describe going away from this limit in 1 second, but strictly in n goes to infinity limit, this describes a Maxwell field coupled to a scalar on S2 cross time. Okay. And so this is the emergent sphere. Now, if n is finite, if n is less than infinity, then the products become star products. The products become star products, which is some so you get a non-commutative field theory. And that's why it's called a fuzzy sphere. Okay, so this matrix quantum mechanics has a classical ground state, and the fluctuations about this classical ground state are a field theory on a sphere. Okay, so this is a completely explicit model of an emergent geometry where there are fields that propagate, quantum fields that propagate on the emergent geometry. So this model, this map. So this is called the Moyal. What I've just done is called the Moyal map, where you map from matrices with matrix multiplication to functions with a star product, and in the n goes to infinity limit, the star product becomes commutative. And one can also check that the SUN gauge symmetry acting on matrices becomes a local U1 symmetry, so a point on the functions, and so it generates that, and also area preserving diffeos. Okay, and that's the gauge symmetry of, it turns out, of this model. But this kind of thing has been known for a long time, going back to in BMN, and there's a semi-classical limit of the BMN matrix quantum mechanics where something very similar happens. Let me see. there's one, yeah, I should say one more thing. So actually, if you're away from n equals infinity, there's sort of
The area,
there's
the area
yeah.
preserving diffeomorphism is just a global symmetry.
No, it's gauged.
It's gauged.
It's
Where's,
gauged.
where's the gauge field for it?
What do I mean to say? What I mean to say, let's see, well, we could write down, yeah, I don't know if I can write down the, yeah, this is a good, there is not one. So the statement is the following, that if you, oh, I'm sorry, you, sorry, let me take you all the way back to the beginning. So here, of course, when I said, I said there was this gauge symmetry. Of course, I've set A0 to 0. Okay, that there was a A0, of course, that in the Lagrangian formula. This is Hamiltonian.
It's just the original SUN.
It is it's the same symmetry. That's
So
correct.
the constraint for it, you say, is something you just impose because you're in some A0 equals 0 gauge. It's the Gauss law. The constraint is the Gauss law for the original SUN.
That's correct. Yes.
Okay.
So one can check that the way, if you act on, I could try to do it. Let's see. It goes something like, so if you want to go to here, and maybe I'll put it in a different color on the side. So if you conjugate x with some u, and you can just see that what's inherited by these AIs is well, the U1 is actually the easiest to see. So yeah, let me say 1 second on the U1. Okay, so sorry. So for example, let me erase this. So for example, so remember xi classical, x was xi classical plus ai, and then you consider the SUN. Let's consider infinitesimal one. So u is e to the it. Okay, and so this is e to the it, xi, e to the minus it. So let's expand these out. So right, this is 1 plus it plus higher orders. What you see is that xi goes to xi classical plus the commutator of it with xi classical plus ai. And so to first order, this guy, under this Moyal map, commutators become derivatives. So this is basically the derivative of t. And that's your Maxwell transformation of this AI field, roughly, very, very quickly. And so if you go to next order, where you also get a commutator of this A, and that turns out to map into these area preserving fields. Okay, so this, you can very explicitly show that this symmetry maps onto a combination of Maxwell and area preserving diffeos on this A field. Good. Yeah, very good. Okay, so all right, so that's the model, okay, that we talked about in earlier papers, and I'm just trying to show you here why the sense in which these matrices give you an emergent geometry with some emergent quantum field theory on it. All right. So what I'm now going to do is I'm going to sort of plan in the remainder is I want to compute spatial entanglement in this model. So in spatial entanglement in the emergent geometry, and I'm going to do it starting from matrices, right, which is the proper non-perturbative, fully regulated finite n version, starting from matrices. Okay, and sorry?
In some sense, you've reversed the historical, I mean, the kind of BFSS type D0 brain large N quantum mechanics came from discretizing the membrane initially. without the new parameter that you have. But you've sort of taken it in reverse, right? In the story.
I guess yes. And from that, let me see. I guess yes. People started from membranes, but I think maybe right. And so this new parameter is kind of a technical crutch that you don't have in BFSS, but you do in BMN. You do have something like it, but that indeed. So that's why this is easier than BFSS. But yeah, I guess the perspective is that the matrices are the fundamental thing, and the space is emergent. Yeah, that's right. But yes, this logic is indeed extremely similar, of course, to how the membrane is discretized. Yes, that's right. Yeah. Right. And I mean, to me, just starting with the matrices just makes it manifest that there's a completely well-defined, simple quantum mechanics model, and everything has to make sense within that model.
Yeah.
Good. And so, and the answer. So what we're gonna just to have something to keep in mind. And so the result is going to be that the Gauss law in the model leads to a large amount of entanglement as due to edge modes, as I'll describe. So the Gauss law requires a lot of entanglement, as we'll see. Right, Gauss law tends to require entanglement, for example, because if the total charge is 0 and you have some positive charge here, you know there has to be some negative charge over there, right? And this kind of correlation contributes to the entanglement. And we're going to get an entanglement. So I'm going to define a cut. We're going to have this sphere. I'm going to make a cut. It's going to be a cap, although it doesn't really don't think it matters too much. But I'm going to make a cut in the way I'll describe. And we're going to calculate entanglement that is going to go like the area, sorry, the length. So the dA is going to be the length of this cut divided by GM, where this is a sort of a Maxwell coupling in the emergent theory. Okay, so it has very much the flavor, I think, of Rutakyanagi, etc., but with Maxwell instead of gravity. Okay, but we'll all of this will be clear. I just want to give you a flavor of where we're heading. Good. So good. So it's reminiscent of Rutakyanagi, and it's also going to be reminiscent of Susskind-Uglum in the sense that this entanglement can be thought of as the number of strings going across this cut that are forced on you by the Gauss law, as we'll see. Okay, so I should tell you how to think about partitioning matrices. And the inspiration for this, the starting point, came from a paper by Das, Kaushal, Mandel, and Trivedi a couple of years ago, and so we're basically going to use their framework in the following way. And so now, the problem with these, once you have more than one matrix, the sort of C equals 1 model is very special. But once there's more than one matrix, the matrices don't commute with each other, and it's not, well, things are fuzzy, and so it's not. You might be unclear how you're going to define a region. But they made the following observation that I think is quite nice. So first, let's think about ordinary geometry. So ordinary commutative geometry. Okay, and then a region. Some region sigma, okay, some subregion that you might care about can be defined by some function of the coordinates that is, let's say, negative inside the region and positive outside. So, for example, if your function was just x1, then this condition would define a half plane, right? If your function was something like x1 squared plus x2 squared, then this condition would define a ball. sorry, x1 squared plus a 2 squared minus 1 would define a ball, right? So a region has a sort of index function, if you like, or no, sorry. There's okay, hopefully this is clear, right? So a function can define a region, a codimension 1 region, right? Sorry, crucially. Is that what I want to say? Well, a region with a codimension 1 boundary is defined by a single function. So, okay, in particular, f sigma of x equals 0 is the boundary of the region. Then what Daz et al. Proposed doing is uplifting to matrices, this function to matrices. And so you define a single matrix F, which is whatever your function was, but now you put in, you put in the big matrices. Sorry, this should have been little x. So you take your coordinates and you replace them with the matrices, right? So for example, to a half plane, if you want to partition a plane in half, you would choose F, the matrix, just to be x1, one of your matrices. Okay, so what's nice about this is that you associate a region with just a single matrix that's a function of the other matrices, but it's just one matrix. And one matrix you can diagonalize, okay, and that can then let you partition up your space of, it gives you a preferred basis in which to partition your matrices. Okay, so the main point is that this associates a region to a single matrix F, which you can then diagonalize. Now, just before I do that, the caveat with this is that obviously the matrices don't commute whilst the coordinates did commute. And so there's an ordering ambiguity when you write down this function, right? So there will be choices of little f that are identical classically, but are not identical in the non-commutative geometry, right? So, so there's an ordering. So just before I diagonalize, let me say in brackets, there's an ordering ambiguity, which was not really addressed well, it wasn't addressed by Daz et al. So there's an ordering ambiguity. And in fact, this is going to come back. What we're going to see later is that, in fact, we need to smear over the non-commutativity scale. And that just makes sense, right? So if you have some non-commuting coordinates and you want to define a region, you shouldn't be able to define the region with an accuracy bigger than the non-commutativity, right? It's like in quantum mechanics, you can't localize things in X and P at the same time because they don't commute. And so you should expect to have to smear before you can define proper subregions. And we're going to see very explicitly that we have to do that. And what this smearing will mean is that this ordering ambiguity is irrelevant because it's going to be smeared regions that we're going to talk about. And the smearing scale is going to be such that it washes out the non-commutativity. Okay, and so, but this is an important conceptual point that you don't look, when locality is emergent, you have no right to expect absolute locality, right? There's going to be a scale at which the locality will break down. That's the non-commutativity scale. And so we should smear all our field theory observables over that scale. Okay, so we'll come to that. We'll come to that later. I'm mentioning it now in case you were worried about the ordering ambiguity. But so again, once again, a single region is associated to a single function. That single function is associated to a single matrix. And a single matrix you can diagonalize and you can order its eigenvalues, right? So F, we can pick a basis where F is F1, F2, F3, all the way to Fn, and these are ordered. So these are the lowest eigenvalues to biggest eigenvalues. And there's a basis of eigenvectors where F takes this form. And so the prescription, what Daz et al. Tell us to do, is to take this basis and partition all the other matrices in this basis, right? So let's say take the first m eigenvalues, the lowest m eigenvalues, and that defines. So again, this function f you can think of as level sets, right? For a bunch of regions, and you pick m. That means you pick an eigenvalue that's the boundary of your region, and all of these you're thinking of as inside the region, whilst all of these eigenvalues you're thinking of as outside the region. So f is diagonalized and gives you a well-defined level. So you have enough. Yeah, you're allowed to diagonalize one matrix, and so you have well-defined level sets of this function f that defines a region. Now, all the other matrices, which will not be diagonal in this basis, get block diagonalized, and so there's an xi sigma sigma, an xi sigma bar, where sigma bar is like the complement, and then there are two off-diagonal ones that we can call this. And so the idea is then that these are degrees of freedom in your region. These are degrees of freedom in the complement. And of course, all the fun has to do with these guys that are in both. And they're very analogous, as we'll see, to Wilson lines. Okay. And so the proposed now, Daz et al., I think, now this is where we're going to sort of, so the main insight that I think is very useful is that you do, given a region, you do have this structure. You can assign a region to a function, and the function defines a preferred basis of the matrices, and you can use that basis to partition all the individual matrices.
So there's some sort of energetics involved here too, right? That the matrices for observables that you'll be interested in that are sort of low energy observables will have small values of x sigma sigma bar and sigma and be mostly in the block diagonals. Is that fair?
Let me think about that. So there was not any energetics in strictly what I've done, but then there's a question of when you expect this to be useful.
I'm just thinking on an observable, which is, so if I'm thinking about your fuzzy sphere.
Oh no, yeah. Wait, let me see. You're right. So can we come back to this in 2 minutes
Sure.
for the fuzzy sphere? You're absolutely right that in the fuzzy sphere, there's going to be a sense in which these off-diagonal guys are small. Yeah, that's right, and that will be quite important indeed.
Right. So there, I guess if you're looking at sort of azimuthally symmetric regions like a cap near the North Pole, then your natural F, I guess, is X is the third, is like J3.
That's right.
And so I'm looking for, if I'm looking for something that lives in the polar cap region, it would be something with a J3 eigenvalue, which is, near the maximal J3 and almost commutes with the J3, I guess.
You're definitely on absolutely the right. We're gonna 2 minutes and let's write it down. Yes, you're right. I think basically, yeah.
Okay. So
certainly in these semi-classical non-commutative geometries, it's going to work like that. Yes. Yeah.
Okay.
So what does it out? I think they were actually sort of a bit perturbed by these off-diagonal blocks, and they sort of discussed different things you could do with them. But the approach we're going to take, which was also a very similar approach, was conceptually was taken by Albion Lawrence et al. A couple of years ago, also somewhat similar, is that in gauge theory, it's you have similar problems in a gauge theory, right? If you want to partition a gauge, a Maxwell, any theory with a Gauss law, you have a problem that that this partition is not consistent with the Gauss law, right? Because you're going to end up with a net charge on one side. And these correlations are all about the Wilson lines going from one side to the other, and they lead to a very interesting contribution to the entanglement. So these off-diagonal blocks are going to lead to a very interesting Gauss law entanglement in this model. So they're a feature, not a bug. Is the main thing. So and let me show you this. So these off-diagonal blocks, which look like they're just annoying, okay, because you're trying to partition things into two regions, and these off-diagonal blocks don't want to partition. But I really want to say they're a feature, not a bug, just like in gauge theories. Okay, so let's think about the Gauss law. Okay, so what I've defined for you now is, given a region, which we'll do an explicit example in a minute, you can partition all your matrix degrees of freedom like this. And we're basically going to want to think about the entanglement of these degrees of freedom with everything else. Okay, that's what we're gonna calculate. So let's think about the Gauss law. So these generators G, the Gauss law is also a matrix, and so the Gauss law also breaks up into a series of blocks. And let's think about this block. So the Gauss law, the SUM, this is an M by M block, right? The SUM part of the Gauss law, has two bits, because I'm sorry for this moving around, but if we jump all the way back, maybe I just should have written it down again. But this bit, this Gauss law here, there's a matrix multiplication here. And so there's an internal index that's summed over in this multiplication. And so that index will run over sigma, but also sigma bar, right? So when we multiply it out, we're going to get x, the bit that's in sigma. And so I'm going to call that G hat of sigma bar. This is the bit of the Gauss law that's purely generated by degrees of freedom here. But these also carry SUM charge. And so they appear plus, sorry, I went out of space, x sigma bar I pi sigma bar sigma I minus I sigma bar x sigma bar sigma, right? And this is the internal index. Even though the external index is just sigma, because of the matrix multiplication, you also pick up this contribution. And I'm going to call that Q. And so the Gauss law, that G sigma equals 0, becomes G hat sigma equals Q. Which should be very intuitive, that you have this SUM. The SUM that's generated purely by these degrees of freedom carries a charge from these off-diagonal modes, right? The off-diagonal modes are charged under SUM, right? And so the total of this SUM charge is given by the off-diagonal modes. Does that make sense? I've literally just rewritten the Gauss law. So that's it. The off-diagonal modes are charged under the SUM generated by the diagonal block. Okay, and so this is what the Gauss law becomes. Okay, very good. What does that mean? That means that if in the ground state, these off-diagonal modes are populated, when you trace them out, your subregion, even the full state is a SUN singlet, but the reduced density matrix is going to be in a non-trivial representation of SUM, because you're going to integrate out some charged stuff. Okay, so by the way, in terms of timing, I did start 10 minutes late. Is that right? Do I have 10 more minutes?
Yeah.
Yeah, I think we'll do it. We'll do 10. Okay. So let me just outline the method. Let me just see how much do I have. Yeah, I think. Okay, so just like in gauge theories, there's a problem if you want to define the entanglement entropy of a subregion, which is that there are these Gauss law constraints. And so the physical states in the theory have correlations between the two regions, and you can't just trace one of them out. And so the method that works, has been shown to work, makes sense, is that in a gauge theory context, is that you have to embed your physical state in a bigger Hilbert space where you relax the Gauss law. Okay, so you have to embed your physical state in an extended, what's called an extended Hilbert space, where you relax the Gauss law.
Why can't I take the whatever matrix you're using to define this preferred basis? Why can't I trace everything against that to construct gauge singlets? And just say, I'm interested in, so there's this matrix X whose eigenvalues are defining your partition.
Yes.
So if I take your favorite SUN matrix and I trace it against that X, don't I, isn't there a way I can just within the Hilbert space you started with build observables which are?
Yes, you can. Sorry, no, thank you. And in fact, this is what Daz et al. Do. So you can, but you're just gonna, it turns out you're gonna miss a lot if you do that. And there's a related choice in gauge theory. It's sometimes called it's related to the choice of center. And so you can sort of gauge fix everything if you like beforehand. Right, but it turns out you sort of miss these Gauss law correlations if you do that.
Okay.
But yeah, it's roughly. Let me. What's the sharpest way to say this? So essentially, right. It's easiest to think of it in the usual gauge theory setting. So say you have Maxwell theory or something, and you have some subregion, and you want to keep just the degrees of freedom in this subregion, and you want to trace out everything else. What turns out to be an interesting thing to do is that in your subregion, there are going to be gauge transformations that don't vanish along the boundary. Okay. And it is interesting to keep those because that tells you something about the gauge theoretic correlation with the exterior. And if you sort of gauge fix too much beforehand and don't keep those, you miss some interesting contributions to the entanglement.
Okay.
I also, maybe we can talk. It's a slightly long story, but yeah, right.
Okay.
Yeah, so roughly this what this extended Hilbert space amounts to, okay, it amounts to keeping sort of gauge theoretic edge modes. Okay. Okay, good. So yeah, this is the prescription of what we're going to do. So you embed your physical states into extended Hilbert space, and then in this extended Hilbert space, there are no constraints between these different regions, and you can just trace them out. Okay, so the Gauss law is relaxed, and so you can just trace. So you're gonna we're going to define a reduced density matrix in sigma sigma, which is the trace over all the other degrees of freedom, the off-diagonal ones, and the other sector of psi psi, right? So we take the states, we have a state, right, that did obey the Gauss law, okay? The physical state remains the same. So we're not messing with the states, okay? The state is the same nice physical ground state, but you write down a pure density matrix, you embed this density matrix into a bigger state, a bigger Hilbert space, which you need to do to be able to trace over all these independently, because in the original state, they're not independent. They're correlated by the Gauss. In the original Hilbert space, they're not independent. So you do that, and then you construct a reduced density matrix. What you can show, okay, so this density matrix is charged under SUM. But it needs to be maximally mixed in each representation. So this is something you can show relatively quickly, but I won't. And it follows from the fact that this state obeyed the Gauss law. So what I mean here is that this density matrix has the following structure. You can write it as a sum over representations and of SUM. And in each representation, there's a number which you think of as the probability of your state being in that representation, divided by the dimension of the representation, times an identity matrix of that representation, tensored with some density matrix associated to the representation, where, so this is a normalized, if you like, gauge invariant density matrix. So to come back to that question from a moment ago, if you didn't do this embedding, the only representation that would appear in the sum would be the trivial one. Okay, and so you can do that, but you can also do this. Okay, so this identity. So what this is saying is that your reduced density matrix breaks up into representations of SUM, and within each representation, the gauge theoretic part is just the identity. Okay, it commutes with all the generators in that representation. What this means is that the entanglement entropy breaks up into several bits. This for people who have thought about edge modes, this is a familiar structure. You sum over all the representations. There's the probability that you find yourself in some representation times the log of the dimension, because it's maximally mixed over each representation. And so that's the maximal entanglement. Then there's an entropy which has to do with the smearing over representations. And then for each representation, there's also the entanglement of the sort of the gauge invariant bits that come along with it. And so this, the term that's going to end up being important, it turns out, is this one. Okay, and so this is the entanglement, of maximally entangled edge modes. In a given representation. Yeah, I'm about to run out of time, so let me try to make a quick geodesic to the punchline. So what happens? And let's come back to this. So what happens in this model with the fuzzy sphere is that it turns out there's a single representation that dominates. The probability of this representation is therefore close to 1. Okay, and so the entanglement entropy turns out to be the dimension of this, the log of the dimension of this dominant representation. I want to give you a flavor of how that happens, and it very much relates to the question from a few minutes ago. The generators of this SUM were equal to this charge by the Gauss law. And we had this charge, if you remember, was X sigma sigma bar, I sigma bar sigma minus pi sigma sigma bar x sigma bar sigma. If we're close to the classical state, these x's can be replaced by their classical values. And these are the off-diagonal classical matrices. And now let's remember what these classical matrices were. As came up in this question a minute ago, we're gonna, if we want a cap on the sphere, the natural matrix to partition is this Z1, right? The J3. So in the basis where J3 was diagonal, remember that x plus and minus, or x1 and x2 are given in terms of J plus and minus. And remember that these had the following structure, where they only had entries just below the diagonal. So when you block partition them, there's only one entry in the off-diagonal element. And this is the sense in which the off-diagonal element is small. Also, this entry is quite interesting. Remember, I told you that if this is M, this is the classical, what am I writing here? This is the classical matrix. X1 and X2 have this structure. They only have one off-diagonal entry, classically. And that diagonal entry is M, n minus M square root. And if you're thinking of this direction as Z, it turns out that what this wants to be is the sine of this angle theta, which is in fact proportional to the length of this. So it goes like the length of the cut. And so the sort of boundary geometry is already there in these classical matrices. Hopefully it's clear. If this is a very low rank matrix with only one entry, then this generator is also very low rank. And so it turns out you have a rank 2, which is a very low rank representation, because these X classicals are so degenerate. Okay, and so in words, basically, these okay, I'm going to be very fast. These representations are determined by their Casimir. Which is trace g hat squared. And what we did is we calculated trace g hat squared. We have an explicit formula for g hat on the semi-classical Gaussian fluctuations about the classical state. So what we did is we calculated this Casimir on the semi-classical state. So then we determined the dimension of this dominant representation, and then we determined the entropy, which is the log of this dimension. I'm sorry for going so quickly, but I don't want to keep you longer than I need to. And it turns out that this ends up being proportional to this sine theta, which is the length of this cut. Okay. And just to write, I'm going to write down the precise answer, just so that I've at least done that. Oh, there's some smearing. I'm sorry, I'm going to have to skip the smearing, but you have to smear it. And so the answer for the entanglement turns out to be the length of the cut on the sphere in units of this smearing cutoff, of some cutoff. Just to show there's a real calculation, there's even a square root of 3 pi. There's a dimensionless Maxwell coupling, and then there's actually a log correction that I don't want to lie about. It is there. Lambda to 3/2 delta A. Okay, so the main result of our paper is this formula, and I didn't show you where we got it from, but the basic point is that you have a completely explicit semi-classical state, you have a partition of the degrees of freedom, you have a contribution to the entropy, which is the dimension of the Hilbert space of these edge modes, and we just calculated it, and you get it. So this is an area law with the 1/g enhancement. and a log correction. This log, technically, it comes from the dimensions of these representations are given by various binomials, and you do some asymptotic expansion of the binomials, and there's a log correction to that. Okay, I think I've overrun already, so I'll stop here. Thanks a lot for listening.
Questions?
So, if I look at, so there, let me just ask a general question. If I wanted to then, if I had this, polar cap, and I wanted to say, let me think about observables which are sort of concentrated within that region. I mean, how would you characterize local observables in your construction? This is the general.
So,
and sort of the degree to which.
Yeah. So I think this comes to what you were saying before. So there's given this F. So let's say up to Fm and then Fm plus 1 up to Fn. There's an associated projection, which is 1, 0, 0, right? Where this is M and M. And so you can basically, the observables that are definitely localized in this region are things where you put a theta on each side and you sandwich whatever you want in the middle.
Mm-hmm.
And so this, sorry, no, you got to be a bit careful actually. Yeah. No, you see, it's not actually very natural, right? So what you see that wasn't good enough, what I just wrote. So if you have a theta and then some string of matrices, these
right.
Matrices have internal indices that go over the sigma bars as well, right? And that's the sort of the fact that your trace, you might have some Wilson loop that sort of comes out and comes back in again,
yep.
right? And so if you want to like do a very severe restriction to this region, you have to sort of put thetas everywhere. And so I think the algebra of observables of the subregion are probably generated by these guys, that you take your x's, take your pi's, project them onto the subregion, and then everything you can build out of that. But somehow that's not, that misses these sort of Wilson lines that want to come out and come back in again. And it's when if you want to account for those, then you have to sort of insert these sort of boundary charges that lead to what I'm talking about. But I think the completely correct answer to your question is it's the algebra generated by these observables is the unambiguously associated to the region sigma observables. Does that make sense?
Yeah, it does.
Okay. And yeah, but that's quite a strong restriction.
Yeah, and it's sort of related to a question which I never understood in string theory, which is how do you because you can't keep strings from wandering out of a particular region, especially as you try to take the cutoff away.
Yeah, so I think you don't want to. I think it's somehow not the most natural. So you somehow want to allow flux to go and come back again.
Yes.
But that is an obstruction to partitioning, right? And so to deal with these guys, you need to sort of, and there's sort of equivalent ways of thinking about it. But one is that you have to allow yourself to insert sort of pairs of charges that split the flux tubes that are coming out and coming back in again. But then you have to sew these charges back together again, and that leads to this extra entanglement.
So if I can't localize things within a region, then what am I computing when I'm computing the entanglement?
Yeah, I think a way you can think about it, it's a measure of the it's a measure of the obstruction to local partitions due to the Gauss law. But there's some magic that I must say I have not understood but so there's this whole story about topological entanglement entropy and Chern-Simons theory and stuff like that. So it turns out that if you, which you have to do all this construction for, but it ends up being physical. And so you might have a lattice model that has, let's say it has no gauge symmetry in it, but maybe it flows to a Chern-Simons theory in the IR. So from the UV point of view, there's absolutely no obstruction to just picking a region and calculating its entanglement. But from the IR point of view, there is an obstruction because there's an emergent gauge field, right? And so it turns out that the thing that matches the UV definition are these kind of things that I'm talking about, where you include these edge modes. I do not understand this connection as well as I would like, to be honest. But so to get the topological entanglement, so that's a certain correction, right, to the area law. So in Chern-Simons theory, the entanglement has an area law, and then there's this sort of this finite correction. And to get this, it's crucial to include these edge modes in the calculation.
Okay.
So let me, because I've also grappled with this. I think that purely within gauge theory, it's really a choice. Gauge theory admits this extension where it's a sort of a canonical extension of the theory where you add these edge modes, and this entanglement that you calculate is, I think it's a measure of the obstruction to defining local observables due to gauge invariance. Okay.
And is there some role that's played in what you're calculating by the area preserving diffeomorphism symmetry?
No, a good one. Thank you. In fact, we've gauge fixed. We're actively thinking about that, but no, not at this point. No. In fact, we've sort of gauge fixed them actually, right? So to be able to talk about this particular region is not area preserving diffeo invariant, right? Because that region will get moved around by these diffeos. And so for those, we've done what you wanted to do with the Maxwell and just gauge fixed it essentially. So there's no. The answer is we haven't grappled with that yet.
Very interesting.
Yeah, so I had to rush there a bit at the end. But yeah, I think these off-diagonal modes are, as you said, very, very analogous to strings, right? And that's why it's a bit similar to this Susskind-Oglum story, that this entanglement is basically counting the number.
Well, it's sort of where it comes, right? I mean, in a BFSS/BMN theory, one thinks of, in some sense, the eigenvalues as some kind of D0 branes, but then the off-diagonal elements is some kind of string stretching between the D0 branes. So.
Right, exactly. So I think that's justifiable, heuristically here as well. Yeah.
Very interesting.
Yeah, thanks for all the questions. I appreciate it. I actually have to go to put the kids to bed.
Yeah. Sorry for keeping you.
No, that's fine. It's good. I'll stop the sharing at this point.
Yeah.
Okay. So yeah, thanks for the invite again. I'm not sure who's there, but anyway, thank you.
Yeah. Where am I?
Yeah, behind you. Hi, Emil. Good to see you. Take care.
Yeah, take care.
We can just.